In Huffman encoding, we're given a set of symbols and certain frequencies, and we want to encode a code word for these symbols, such that, okay, so what Huffman encoding does is that it takes the two smallest frequencies and puts them at the bottom. It creates a binary tree, right? Because once we have a binary tree, we can choose going left is 0 and going right is 1. And to construct this binary tree, we want the largest frequencies to have, like, let's say, to have the shortest code word, and then the small ones to have the code words longer. For this to occur, we take these two smallest, the two symbols of the smallest frequencies, and we pair them together. I'm going to add them to make a new node. We call these internal nodes. And the frequency of this internal node is going to be the sum of the frequencies of the two leaves that we had. And once we have this internal node, it becomes a leaf. We can put it into the priority queue. And then we can pop it off now or pop it off later and keep popping off two, pair them together, and keep creating this tree. So the idea is that once I have my initial priority queue contains a set of leaves, which are all just symbols. Now, we want to do this until we only have one node remaining, and we keep taking 2 off and putting 1 back in. We only need to do this. K can only go from n plus 1 to 2n minus 1 certain nodes. So once we reach 2n minus 1, we know we have reached the root. And so what we do in every iteration is that we pop off the two smallest elements based on the frequency from our priority queue. And since if the priority queue is going to contain what we consider leaves, and once we have created a node, and we're going to have the two leaves we just popped out as this new node's children, and the frequency is just going to be sum of those frequencies, and we're going to push it back into our priority queue. So once it's in the priority queue, we don't have to look at its children anymore because we already seen it before, right? So once in priority queue, it's then the new frequency, it's the new node's priority, and based on that, we can either pop it off immediately, like what happened here, or we can wait until sometime later to pop it off. So I have an example where, let's say we have the symbols. We have A, B, C, D, E. Okay, so this is from the book, which usually the frequencies means that they're probabilities. And the sum of the frequencies equals 1. And let's say this is 10 out of 100, 30 out of 100, 16 out of 100, 34 out of 100, and 10 out of 100. Okay, and we want to minimize this objective, right? The cost of the tree. And the cost of the tree is going to be sum of my frequencies multiplied by the depth of that symbol. Which for this proof, for like saying this gives us the optimal cost of the tree. The proof I won't go over here. You'll be covering it in the homework. So let's look at this example and go through our procedure. So we're going to take the two. So we have our priority queue, right? The priority is going to be A, E, C, B, and D. So we're going to pop off A and E, and we're going to create A. We have a frequency, let's just call it use 10 for because it's easy right now, right? And both A and E have frequency of 1/10. Right. Now what it does is that it's going to create this node. So this is popped off. And what happens is that because this node has a frequency of 20, it gets added back in the priority queue. And I'm going to call this X. And the X actually gets right into this part. So in the next iteration, I'm going to pop off both C and X, right? So pop this one off, and I'm going to create another pair here, which will be C. And it has a frequency of 16. And I pop off X, right? Together, they form a new vertex. So I'm going to use this box. I'm going to use the box as an internal node. In this internal node Y, we now have 36 as my frequency. So I add it to the priority queue, right? So both these are off. But now, when I add it to the priority queue, it comes after the next two, right? So y comes over here. So we have to pop off both b and d before we can pop off y. And when I pop off b and d, I create a tree b and d as 30 over here, and d as 34. So I'm going to create this internal node. Let's call it z. And it's going to have a frequency of 64, right? And then I push it back in. Now I can pop off y, right? So y, when I create internal node and I push in priority queue, it is not always the fact that it's immediately propagated. Does not always mean that it gets popped out immediately. Like in this case, it could be popped out immediately like here, or it could wait until later like with y over here. So now we take z and we take y, and we have our root, and its frequency should be 100 or 1, right, in terms of percentages. So here's a binary tree where we have an example that I create an internal node and I get popped off immediately, or I have created an internal node and it gets popped off sometime later in my tree. Okay. So now let's look at the discussion 6 proofs, which I think are pretty, you want to kind of think about the properties of a binary Huffman tree. So let's have these frequencies. We want to see, okay, what is the longest code word it could possibly be? So think about our procedure. In the very first in the very beginning, our priority queue only contains leaves, right? So these leaves always means they are symbols. And internal nodes, they don't have a symbol associated with it. So we have n leaves. And at the very bottom, we must take 2 of the leaves and put it at a certain layer. Right? So the code word, how the code word encodes is that at every layer, I add a length to it. Right? So in this case, I could be, let's say, 0 and 1 going this way. I have 0, 0, 0, 0, 0, 1, 0, 1, where's C? Okay, 1, 0, and 1, 1. Right? So each time I go through a layer in a tree, I'm going to add an extra length to that code word. And what's going to happen is that since I have n leaves, and the bottom layer has to have at least 2 leaves, then you're left with n minus 2 leaves to give you the longest code word. And in order to do that, what's going to happen is that I take 2 leaves, merge it together, and I put it in priority queue, and I'm going to pop it off back immediately so that I add another code word, put these 2 together, put it in my priority queue, and pop it off immediately again. Right? So in this case, I take B and C, push it in my priority queue, pop it back off immediately, so that at this level, I can only create one more, I can only add in one more leaf. And if I minimize the number of symbols I add in, then this tree is going to be as long as possible, as deep as possible. And if we maximize this height, we'll maximize the coder, right? So what's going to happen is that I take the 2 leaves, that's always going to be my base layer. At every single layer, I take one more, and so on. So the length of my code word is this depth over here. And it has to be n minus 1 as the maximum length. Right? And it's n minus 1 because I have to have 2 leaves at the very bottom. If there are n, if I have code word, if I have length n, then I'm going to have n plus 1 leaves, right? Because I can't have n length, code word of length n, and I have only n leaves. Because one of these can't be matched up with another leaf, right? It's contradiction. If I have length n or more, then I have to have more than n plus 1 leaves. And so our longest code word in a Huffman tree is going to have length n minus 1. So this is an example where it works. Or you can think of an example where what you do is you take these 2 frequencies, you add it together, and you're going to add one more in the next step like that. Right? I think one example is I take 2 of n minus 1. I take frequencies 2 n minus 1 like this. Oh, I think it's n minus 2. Right, n minus 2. And so I have 2 leaves, so these 2 leaves will always be matched together. And here I take n minus 3, right? Let's see if this was 1/8, 1/16, 1/16. If I add these frequencies together, yeah. So if I add these 2 frequencies together, I'm gonna get this next one, right? And then adding this 2 and this 2 together should give me this one, and so on. So I get 1/8, right? So I get some part over here. If I sum these up, I get 1/8. Adding them together, I get 1/4, and then 1/12. And if you just keep pairing these together, you can only add 1 leaf in at every layer. Now let's look at this, and the sum of this is always going to be, so the sum is going to be 1, right? Because we're talking about probabilities, and there's going to be a length of n, right? So this is 2 to the n, 2 to the 1, 2, 3, 4. So we're going to have n minus 1, and then n minus, so we're going to have n minus 1 elements. Oh, so up here we get n minus 2 elements, and then add this extra one, we get n minus 1 elements. And here's an example of getting a tree with the longest encoding possible. Now, so here we're saying that if all my characters have a frequency of less than 1/3, then we have to have a code word of length 1. Now, most Huffman encoding proofs of these properties, we want to make use of contradiction, right? Contradiction. So to set up a contradiction, what we do is we always take, so we're saying that this guaranteed to be no code word of length 1, right? So what if I have a code word of length 1? And I'm going to call this x, right? Such that we're saying that if all the characters occurs with frequency less than 1/3, right? So let's say the frequency of x is less than 1/3. Now, what's going to happen is that if I have 1/3 over here, what it means is that I can't have, so let's say I have 2 more symbols. I have y and I have z. Right? So if this is 1/3, this internal node on this side must be greater than 2/3 in order to get 1 up here, right? And if this is 2/3, then one of these is greater than 1/3 and one of these is less than 1/3. And this is a contradiction because this can't happen. We're always summing up the 2 lowest frequencies together, which have to be these 2, right? So that means these 2 cannot be summed up together to create this internal node of 2/3, and thus we cannot. So this means we have a contradiction in our y and z merge. So thus we can't have a code word of length 1, right? Can't have leave from root node code word of length 1. All right. So what about when are we guaranteed that there has to be a code word of length 1? So here we're saying that if there was some character with frequency more than 2/5, then we guarantee with length a length of the code word of 1. Now, so let's set up our contradictory Huffman binary tree. We have remember we cannot have a code word of length 1 in our setup. So we have a full tree like this. Okay, suppose we have S over here, and this is greater than 2/5. If this is greater than 2/5, then this internal node is always greater than 2/5, which means this side y has to be, so this internal y over here is less than 3/5, but also greater than 2/5 as well. Otherwise, we can't get this frequency of 1 up there. Now, if this internal node is less than 3/5 but greater than 2/5, then this y frequency must also be greater than this one over here, right? So the frequency of this symbol x is now less than 1/5. Otherwise, we can't. If this is greater than 1/5, then this can't be greater than. We can't have this less than 3/5 over here, right? Because if this is greater than 1/5, this is greater than 2/5, then this one has to be greater than 3/5. But we're saying that this is greater than 2/5, this is greater than 2/5, and with this y over here under this inequality, this x must be on this side with less than 1/5. So now what's going to happen? So y was, because we can't have a code word with length 1 in our contradictory assumption, we're saying that y was made up of two leaves. And these two leaves, y and z, right? And let's suppose, make it easier, we have this as less than 3/10 and this as less than 3/10. So that together, the summation is going to be less than 3/5. But 3/10 is less than 2/5. That means the x must have been merged with one of these w or z, whichever is smaller, but in this case they're the same, right? Whichever is smaller, we should have merged with x. So now we have a contradiction as well, right? Contradiction, we have an impossible merge between x and y, between s and x. So therefore, need to have length 1 code word. Right, you see how most Huffman encoding proofs involves with these kind of contradictory assumptions. And a hint I'll give you on the Huffman proof on the homework is to think about what happens if I take a node here and I take one of these here and I swap them, right? Or these two, x and fz. If these were swapped, then we know it would have made, like, if you swap them and the cost decreases, it's going to be better for your overall cost, right? So in terms of Huffman encoding, you can make use of the exchange argument. And the exchange argument, you're switching between two leaves at two different depths. And by exchanging, you want to prove that the cost is going one way and you can get an optimal tree with this algorithm.